recording of this one. I can say, all right, so let's talk about analyzing input data. This is something that really helps me understand more of the weaknesses of this. If you think about political polls, you survey people, then you try to guess who the president is going to be, and as we know, frequently the answers are totally wrong. They say, how can they be so wrong at doing this thing that just seems scientific? How hard can it be? It can be a lot harder than you might imagine. So here, in this one, you got data about housing prices in California. So you have a whole bunch of data, a lot of data in here. You have total number of rooms, bedrooms, the population. These are in like zones of California, sort of like counties. Then you have the income in that area, and you're going to try and predict the house value from all these other parameters. So you can get statistics of these parameters. This is what you have to do. When you feed data into an AI, you have to clean up and modify the data in the first place with human judgment to prepare it for the AI to work on it, because real data is kind of messed up. So if you plot these things and see how popular certain things are, of course, latitude and longitude are not Gaussian distributed in California. There's a population center near Los Angeles, another one near San Francisco, and that's it, right? So latitude and longitude have two peaks. The housing median age has this strange distribution, which I imagine means there are certain periods of time, like after World War II, when there was a boom in building houses, then there was less houses built and stuff like that. So again, not a clean distribution. So you take your data, break it up into training and test sets as usual, and now you have to consider biased sampling. Now, when you break your data into a training and a test set, the first thing you might do is say, take 20% randomly of the data and set it aside for later. The problem is, if there's a parameter there that is important, you might have a biased sample. So consider something that's sex-related, related to whether people are male or female. In America, 51% of people are female. So if you took a random sample, the most likely thing is 51% of them would be female, but it's quite likely that they have only 49 or 48% female or 54% female in your test set. And if that is an important parameter, it's biased. It's not going to be representative. So instead of doing random sampling, it's better to do stratified sampling. So we know that income of people is a strong predictor of the housing cost. So instead of randomly sampling the income, we put the income in 5 categories, and then we carefully choose the right percentage of each of those 5 categories. And that's stratified sampling, so that now you split the data, and now you can see the training set has 35% in category 3 and 31% in category 2, and so does the test set, because I took each of those bins and chose just the right number to match it. So that's a consideration. And if you made it random, that wouldn't be true. So now another thing you can do is plot the data to try to see the trends. So here's the first thing of plotting all the data. The problem is the blue dots get so dense you can't see how many blue dots there are, so transparent dots are much better to see the real distribution. Then you might want to include the population and the price with colors and so on to try to see more of a pattern. And of course, you'll see that all the expensive houses are on the coast in San Francisco or LA, and the houses inland are much cheaper. And then now the main thing, though, is correlations. This is where you begin to see the suffering here. So this is just the probability of median house value. Here is the correlation between income and the house value. And of course, this is a strong predictor. In areas where people have more income, they pay more for the house. So you see a trend here, a nice line. So that's good. And these other things, you see less correlation. So now you can give it a correlation coefficient to see how predictive each of these things are. And now it'll turn out that in addition to being, often what happens is, even though the individual parameters are not very predictive, a combination of parameters is predictive. And this is going to come back over and over again in machine learning. You don't take the raw data the way it comes. You often combine the raw data, like square it or cube it or multiply or divide two things together to create a new measure that is more useful. And that wouldn't make sense if they were really independent measures, but they're not. They're connected to each other in ways. So it turns out here that there's a bedrooms ratio, which is the number of bedrooms divided by the number of rooms. That's more predictive than just the total number of rooms of house value, that sort of thing. But another thing to notice is flaws in the data. Here's median income against median house value. Well, notice you have the house value go up to $500,000, and then you just have a huge glut of points at $500,000. So obviously, they didn't actually measure the house value. They just used $500,000 as a ceiling. So we don't actually know what the real cost of these houses are, and if we leave that data in there, the model is going to learn some bizarre behavior which is not representative of the real population. And look at this, there's a glut of weird data at 350 and at 450. So apparently somebody was rounding off data here or something. You don't really want your model to learn to hit these points because those points are not real. That's some kind of artifact of the data. Although you can't prove it and you don't really know how this data was collected, you take a human and you make judgments. Well, let's throw away these points. Let's throw away those points. We won't need to throw these away. We'll just move them into the middle where they belong. That's how you get in trouble. It's not science. It's like art. Humans look over the data and decide what part of this data do I trust that's helping me get where I want to go, and what part of it looks like an error. And that's why you get these supposedly scientific processes that tend to just produce what they wanted to see. It's kind of inescapable. And here's the attribute combinations. Here's the correlation coefficients. The only thing that's really strongly predictive is income. The correlation coefficient of 1 means you can predict things, 0 means no correlation at all, and it's all pretty low. But bedrooms ratio is 25% predictive, which is much better than any other parameter that in income. So that's one thing to consider when they say we used machine learning to analyze this data. Well, that's not true. You used humans to massage and modify that data as needed to simplify it to where it was a problem you think machine learning could solve.